In 2008, a paper was published online by a person or group using the name Satoshi Nakamoto. It was titled, Bitcoin, a peer-to-peer electronic cash system. It described a radical new way to send money over the internet directly from one person to another without needing a bank. In this video, we're going to walk through that original paper, section by section, to understand not just what Bitcoin is, but why it was designed the way it is. To understand Bitcoin, we first have to understand the problem it was designed to solve, and that problem can be summed up in one word: trust. For decades, commerce on the internet has relied almost exclusively on financial institutions to act as trusted third parties for electronic payments. When you buy something online, you aren't paying the seller directly. You're paying a bank or payment processor who then pays the seller on your behalf. This system works most of the time, but it has what Satoshi calls inherent weakness. The biggest weakness is that transactions are never truly final. Financial institutions have to mediate disputes. This means payments can be reversed. While this protects buyers from fraud, it creates a huge problem for sellers. The cost of this mediation gets baked into every transaction, making small, casual payments, like tipping a creator a few cents for an article, impractical. Sellers also have to be wary of their customers collecting more information than they otherwise would, and they simply have to accept a certain amount of fraud at a cost of doing business. In person, we solve this with physical cash. It's a direct, non-reversible exchange, but before Bitcoin, there was no way to do this digitally without a trusted party in the middle. What was needed was a system based on mathematical or cryptographic proof instead of trust, a way for any two people to transact directly with payments that are, for all practical purposes, irreversible. This would protect sellers, and as we'll see, escrow mechanisms could still be used to protect buyers. So, how do you create a digital coin? Before we can understand how to transfer one, we need to understand the fundamental tools of cryptography that make it possible: public and private keys and digital signatures. Imagine you have a secret special key that only you possess. This is your private key. From this private key, you can generate a public key, and from that, a public address, like a mailbox you can share with anyone in the world. People can send things to your public address, but only you, with your unique private key, can unlock the mailbox and access what's inside. Your private key has another power. It can sign messages. By applying your private key to a transaction's data, you create a unique digital signature. This signature proves two things: that the message hasn't been tampered with, and that it was authorized by the owner of the private key. Anyone with your public key can verify the signature without ever needing to see your private key. With these tools, we can now define what Bitcoin actually is. In the Bitcoin system, a coin isn't a single file. Instead, as Satoshi Nakamoto wrote, an electronic coin is a chain of digital signatures. It's a continuous, verifiable chain of ownership. Let's watch this chain being built. Here's an existing transaction where owner 1 is the current owner of the coin. To send the coin to owner 2, owner 1 constructs a new transaction. This transaction contains two crucial inputs. First, a hash referencing the previous transaction, and second, the public key of the next owner, owner 2. To authorize this transfer, owner 1 uses their private key to sign the new transaction data. This action creates a unique digital signature. Anyone on the network can verify the transaction is legitimate by taking owner 1's public key from the first transaction and checking against the signature of the new one. The signature is valid, so owner 2 now officially owns the coin. Now the process simply repeats. To send the coin to owner 3, owner 2 constructs a new transaction. It again contains a hash of the transaction before it and the public key of the new owner, owner 3. Owner 2 uses their private key to sign it, authorizing the payment. And just like before, owner 2's public key can be used to verify the signature, providing the transaction is valid and adding a new link to the chain. By linking each transaction back to the one before it, we can create a public history of the coin's journey, but this leads to a critical problem. The payee can verify the chain of past owners, but how do they know that one of those owners didn't transfer the coin to someone else before they transferred it to them? This is the double spend problem. How can the network be sure that Allison promised the same coin to both Bob and Charlie? A traditional bank solves this by being the central authority. They see all transactions and decide which one came first. But to do this without a trusted party, we need a different solution. As Satoshi writes, transactions must be publicly announced. We need a system for everyone to agree on a single shared history of the order in which transactions were received. This is where the idea of a timestamp server comes in. The solution begins with what Satoshi calls a timestamp server, but to understand it, we first need to understand its most important tool, the cryptographic hash. A hash function is a mathematical function that takes any input, a document, a picture, any amount of data, and spits out a unique fixed-length string of characters called a hash. Think of it as a digital fingerprint. This fingerprint has three crucial properties. 1, it's deterministic, meaning the same input will always produce the same output. 2, it's a one-way street. It's easy to calculate the hash from the data, but practically impossible to figure out the original data from just the hash. And 3. Any change to the input, even a single comma, will result in a completely different hash. This is called the avalanche effect. Bitcoin uses this powerful tool to create a public chronological record. The network bundles a group of recent transactions together into a data structure called a block. This block is then timestamped by taking all its data and hashing it, creating a unique fingerprint for that block of transactions. But here's the crucial innovation. As the animation shows, to create the hash for the new block, the system also includes the hash of the previous block. This creates a chain. Block 2 is linked to block 1, block 3 will be linked to block 2, and so on forever. This chain of hashes is what makes the history of transactions tamper evident. If an attacker tried to go back and alter a transaction in an old block, the hash of that block would immediately change. The change would break the link to the next block and next, creating a cascade of broken links that the entire network would immediately reject. Each additional block or timestamp reinforces the ones that came before it. But this raises a new question. In a decentralized network with no one in charge, who gets to create the next block and add it to the chain? The answer lies in a concept called proof of work. To implement this timestamp server on a peer-to-peer basis, Bitcoin uses a similar system to Atomback's hashback called proof of work. This system solves the problem on how to reach a majority decision without trusting anyone. If voting were based on IP addresses, an attacker could just create thousands of fake nodes. Instead, Bitcoin uses a one CPU, one vote system where voting power is tied to a computational power. This is done by making the process of creating a block difficult and resource intensive. It's a competition. Here's how it works. The proof of work involves a simple but intensive process, finding a special value called the nonce. Inside each block, along with transactions, are two key pieces of data: the hash of the previous block, which links them together in a chain, and this special number, the nonce, that miners change over and over until a block's hash meets the network's difficulty target. The goal is to find a nonce that, when combined with the rest of the block's data and hash, produces a hash that starts with a specific number of 0 bits. Because of the avalanche effect, the only way to find it is through brute force. Miners test the nonce, hash the block, and check the result. If it's not low enough, they increment the nonce by 1 and try again, millions or billions of times per second. This is the work. Once that CPU effort is spent, the block is sealed. It cannot be changed without redoing all of that work. Because each new block contains the hash of the one before it, changing a past block would mean redoing the work of that block and every single one that came after it. An attacker would have to outwork and outpace the entire honest network, a practically impossible task. The majority decision is represented by the longest chain, the one with the most proof of work invested in it. So we have transactions, blocks, a chain, and proof of work. Now let's put it all together and see how the network actually operates step by step. Step 1. New transactions are broadcast to all nodes. When you send a payment, your wallet broadcasts the signed transaction to the nodes it's connected to, who then broadcast it to the nodes they're connected to until it propagates throughout the entire network. Step 2. Each node collects a new transaction to a block. Each miner on the network gathers up these unconfirmed transactions from their transaction pool and assembles a candidate block. Step 3. Each node works on finding a proof of work for its block. Now the race begins. Every miner starts the proof of work process, hashing their unique block header over and over, hoping to be the first one to find a hash that meets the difficulty target. Step 4. When a node finds a proof of work, it broadcasts the block to all nodes. As soon as a miner finds a solution, they win the round. They immediately broadcast their completed block to the rest of the network. Step 5. Nodes accept the block only if all transactions in it are valid and not already spent. When other nodes receive this new block, they quickly check it. Is the proof of work valid? Are all the transactions inside it legitimate and not double spends? If everything checks out, they add the block to their own copy of the blockchain. Step 6. Nodes express their acceptance of the block by working on creating the next block in the chain, using the hash of the accepted block as the previous hash. This is the most important step. By accepting the new block and choosing to build the next block on top of it, the entire network reaches a consensus. This all sounds like a lot of work, but why would anyone dedicate expensive computer hardware and electricity to participate in this network? The answer is incentive. By convention, the very first transaction, every new block is a special one. It's called the Coinbase transaction, and it creates brand new coins out of thin air which are awarded to the miner who found the block. This is the block reward. It's how new bitcoins are introduced into circulation. Analogous to gold miners expending resources to pull gold out of the ground. There's a second part to this incentive: transaction fees. If you want your transaction to be processed more quickly, you can attach a small fee. Miners are incentivized to include transactions with higher fees in their blocks. The white paper notes that once all Bitcoins have been mined, the incentive system can transition entirely to transaction fees, ensuring the network remains secure forever. As the blockchain grows, storing every transaction ever made becomes a problem for disk space. The white paper proposes a clever solution to this using a data structure called a Merkle tree. Instead of hashing all transactions together in one big lump, they are hashed in pairs. First, each individual transaction is hashed, then the resulting hashes are paired up and hashed again. This process continues, pairing and hashing up the tree until you are left with just one single hash to the top. This final hash is called the Merkle root or root hash. This Merkle root is the only thing that gets included in the block header. It acts as a single secure fingerprint representing all transactions in the block. If even one transaction is changed, the Merkle root will change completely, invalidating the block's proof of work. Now here's how it saves space. The Merkle tree has another powerful benefit. It makes it possible to verify payment without needing to run a full network node and download the entire blockchain, which can be hundreds of gigabytes. This is called Simplified Payment Verification or SPV. An SPV client, or lightweight wallet, works by downloading only the block headers of the longest proof of work chain. Remember, these headers are very small. Now let's say this user wants to verify that a payment they received, transaction 3, is included in the blockchain. They don't have all transactions, so they can't rebuild the Merkle tree themselves. Instead, they can request a Merkle proof from a full node. This proof consists of only the hashes needed to connect their transaction all the way up to the Merkle root. The SPV client takes its transaction hash, combines it with the provided hashes from the proof, and recalculates the Merkle root. If the result matches the Merkle root in the block header, the user knows their transaction is part of the block and has been accepted by the network. They can see how many blocks have been built on top of it as further confirmation. This allows for secure, lightweight wallets that can run on devices like mobile phones. So far, we've been talking about a coin as a single unit, but in reality, you rarely want to spend the exact amount you received in a previous transaction. To handle this, Bitcoin transactions can have multiple inputs and outputs, allowing you to combine smaller amounts or split up a larger one. Think of it like paying with cash. If you want to buy a $5 coffee but you only have a $20 bill, you give the cashier the $20 the input, and they give you back $15 in change, an output. The coffee is the other output. A Bitcoin transaction works the same way. A transaction can draw upon multiple previous transactions as its inputs. It then creates one or more outputs. Typically, there will be one output for the payment to the recipient and a second output that sends the change back to an address that you control. Any part of the input value that isn't accounted for in an output is treated as a transaction fee for the miner. With all transactions being publicly announced, what about privacy? The traditional banking model achieves privacy by limiting access to information. Only you, the person you're paying, and the bank can see the details. Bitcoin's public ledger precludes this method. Instead, privacy is maintained by keeping your public keys anonymous. The public can see that an amount was sent from one address to another, but without additional information, there's nothing linking those addresses to real-world identities. It's like a stock exchange ticker where you can see the trades but not who made them. To further enhance privacy, the white paper recommends using a new key pair, a new address, for every transaction you receive. This prevents different payments from being easily linked to a common owner. How secure is the system really? An attacker can try to reverse a transaction by secretly building a parallel fraudulent chain. This creates a race between their chain and the honest one. The gap between them, Z, is the number of blocks the attacker is behind. To succeed, the attacker must close this gap and eventually overtake the honest chain. This race is the classic gambler's ruin problem. Let P be the honest network's chance of finding the next block, and Q be the attacker's. If the honest network is stronger, P is greater than Q, the attacker's probability of ever catching up drops exponentially as the gap Z increases. If the attacker doesn't get lucky and make progress early, their chances quickly become vanishingly small. But how long should a merchant wait? To find the true probability of an attack, we model the attacker's likely progress with a Poisson distribution. This lets us calculate the risk by summing the probabilities for every possible scenario. This gives us a much more precise and realistic measure of security than simple gambler's ruin formula alone. The numbers show how security improves with each block. For an attacker with 10% of the network's power, after just 6 confirmations, the chance of reversal is tiny, 0.024%. A stronger attacker with 30% power would need around 30 confirmations to reach a similar level of security. The conclusion is clear. With each new block, reversing a transaction becomes exponentially harder. And so, we arrive at the end of the topics of the Bitcoin white paper. Satoshi Nakamoto proposed a system for electronic transactions without relying on trust. It starts with a framework of coins made from digital signatures, but solves the crucial double spending problem by using a peer-to-peer network to record a public history of transactions. This history, the blockchain, is secured by proof of work, a system that makes it computationally impractical for an attacker to change the past, so long as honest nodes control a majority of the CPU power. The network is robust in its unstructured simplicity. Nodes can leave and rejoin at will, and they vote with their CPU power, expressing their acceptance of valid blocks by working to extend them. As Satoshi concludes, any needed rules and incentives can be enforced with a consensus mechanism. It was a proposal that launched a revolution, and it all started with the topics in these 9 pages.